Another day, another question and solution on the certified Q&A for the Google Cloud Platform Associate Cloud Engineer. It's very important to the process of understanding Google Cloud and passing the certification exam that you go through the question and attempt answering it yourself first. So pause the video, work through the question. We'll catch up in just a little while and I'll show you how I do it. In this project scenario, somebody's approached your company asking for your guidance on choosing the right storage system within Google Cloud. This company has a mission-critical application that serves users globally. You need to select a transactional relational data storage system for this application. Which two products should you consider? BigQuery, Cloud SQL, Cloud Spanner, Cloud Table, or Cloud Data Store? Before we discuss within our team to figure out what is the suitable storage system, let's find out the key terms. We need to be able to serve users globally, all around the world. The data needs to be transactional and relational. Okay. What we will do is we will create a table and mark off the products that suit each of these requirements. First, which of these support relational data? Before that, what is relational data? The relational database was defined by somebody in IBM in 1970. Edgar Cord codified what defines an RDBMS, or a relational database management system, into a bunch of rules called Cord's 12 rules. Today's commercial databases typically implement only a subset of these rules. In a relational database, data is in rows, or records or tuples, and columns of attributes, and these are all part of a table. The table themselves are related to each other through common columns. So if you had a user column, maybe that person's user ID is used to connect that user's name to probably his salary details and account details in another table. So they will have that common ID that connects the two tables, and that's what gives a relationship between this data. After Ted Cord wrote about the relational model in 1970, a couple of other people at IBM, Donald Chamberlain and Raymond Boyce, they developed a way to interact with the relational model. This eventually came to be called the structured query language, or SQL. Ted Cord had defined operators to work with RDBMS, most of which are supported by databases today. For example, select and union. Commands like insert, update, delete, they modify data, and select queries the data. Today's SQL has become a standardized way to work with relational data. This is great because irrespective of how the database are implemented, we have a consistent way of working with the database, which is using SQL. Relational data, typically accessed via SQL, is referred to as structured data because there is a predefined schema or structure with the tables and columns and rows. This is a flowchart that helps you choose the right storage option. You need to be thorough with this flowchart. Looking at this flowchart and just marking off the portion that is required for relational data, which is accessed using SQL and typically structured, we can see it is this highlighted portion on the top left. So the three options we have are BigQuery, Cloud SQL, and Cloud Spanner. Big Table and Data Store are not relational data. Next, let's look at transactional data. What is a transactional database? So some updates in a database, say like a financial transaction, involves multiple steps that need to be done together. When you have two accounts and you need to move funds from one account to another, you should read the original account, deduct a value from it, take that value and add it or deposit to the destination account and update the balance there. It is very important to have all of these steps happen or none of them. So after all happens, you can do a commit and treat that as a logical unit. Or if even one of them fails, you have to roll back all of them. It is not allowed to have an intermediate state. The transaction has to be complete. It is not allowed that you deduct an amount from the source, but between deducting it and depositing it into the destination account, if there is a failure, you cannot have the state where money is already deducted here but not added to the other destination account. So this is a all or nothing operation. When a sequence of database operations satisfies what are called the ACID properties, ACID, then it is called a transactional database in database terminology. The letters of ACID stands for atomicity, consistency, isolation, and durability. What is atomicity? Each transaction is a single unit. Like we did for the fund transfer, that whole fund transfer is treated as single unit. You can't do only just part of the withdrawal and not do the deposit. So either it succeeds or fails completely. When this is treated as a logical unit, it means that while the transaction is in progress, another request should not be able to see that intermediate state. A person trying to figure out the balance of an account should not see it after the withdrawal of an amount, but before it is deposited to the destination account. So no intermediate states are allowed. It is a single unit transaction. C stands for consistency, which means that a transaction in a database has to go from one valid state to another valid state. Which means that when a transaction completes, it should be in a state that is valid according to all the constraints defined by that database. For example, the data type should be as defined in the columns. The data size should be as defined in the columns. So those constraints have to be met. If there are cascade operations, update or a change in one row has to make a bunch of other cascade or ripple changes in other parts of the database, those have to happen. Triggers similarly, and any combination of constraints, cascade triggers, all of them have to be in a valid state after the transaction is complete also. So in consistency, it has to go from one valid state to another. I stands for isolation, which means that when a bunch of transactions are happening concurrently on a database, which is very much a possibility, because these databases are being accessed simultaneously, probably all across the world, from different applications and different users. So these transactions are going to happen concurrently. Isolation means that when these transactions happen concurrently, they should result in the same state as if those transactions happen sequentially. Doing a transaction or multiple transactions concurrently should not result in what is called a race condition. A race condition where, depending on who got there first, if the results are different, then that would not be acceptable. D stands for durability, which guarantees that once a transaction is completed, it will remain on the system even in the case of, say, power failures or system failures. This essentially means that all completed transactions are recorded in persistent storage, so that the next time it comes back up, next time the system comes back up, you're able to pull up all the transactions that happened and they should all be in a valid state. We also hear about this difference between an OLTP and a OLAP, an online transaction processing system and an online analytics processing system. What are the differences between these? So OLTP typically has recent data, things that are happening currently, things that are happening real time. Whereas an analytics processing engine usually has historic data. You want to be able to go back in time and figure out statistically or with data over many years, what are the patterns in the data, essentially analytics. An OLTP is going to be optimized for inserts, updates, and deletes because this is going to happen at real time. It is going to happen often, and therefore these OLTPs have to support transactions and changes to the data like insert, update, and delete. An OLAP, on the other hand, is optimized for read. You're going to have large amounts of data and you want to be able to read it quickly. An OLTP scales well to gigabytes or terabytes of data, whereas an OLAP scales well to petabytes of data. So typically you're dealing with way larger data when it comes to an analytics engine as opposed to a transaction engine. An OLTP is difficult to scale horizontally. When we say scale horizontally, there are a couple of ways in which you can increase the throughput in a system. Either you get more powerful machines with faster CPUs and more memory, which means you're scaling it vertically. Whereas a horizontal scaling means you get maybe cheaper machines, but you keep adding machines when you want to achieve greater throughput. Transaction processing engines typically do not scale horizontally very well because it means that there are replicas of this one system, and when you lock parts of the system for an update, you need to make sure that all the other replicated systems are also locked for that transaction. That is difficult to achieve at global scale. An analytics engine, on the other hand, mostly we want to read from it, and it will be okay to replicate the data easily without having to lock the machines or lock the database, and therefore it's easy to horizontally scale. OLTPs are mostly relational, whereas OLAPs can be relational or it could be columnar or other storage format. OLTPs are dealing with current data, which means you're typically going to deal with real-time data inserts. As soon as a transaction or a fund transfer is initiated, you want that to happen immediately. Analytics engines, on the other hand, because they're working with historic data and not always do they need the absolute current data, it is okay to delay the information entering the analytics engine, typically as batch insert, maybe end of the day, end of the week, maybe after a few hours, or it could be even after minutes, but it doesn't have to be real time. The OLTPs we have on Google Cloud are Cloud SQL and Cloud Spanner. And the OLAP we have on Google Cloud is BigQuery. Looking at this chart now, we already know that our data is structured, SQL, relational, and we have to choose between SQL, Cloud Spanner, and BigQuery. Now that we know about transactional databases, we have learned that BigQuery is an analytics engine that is optimized for read as an OLAP, whereas what we want is transactions. So the two databases that suit transactions or as an OLTP are Cloud SQL and Cloud Spanner. So we tick those two boxes, but we leave the others empty. Just for your additional information though, data store and file store support ACID transactions. So also does BigQuery. But these are not considered transactional databases. Let's confirm what we learned about Bigtable a little bit and also about OLTPs and what is available as OLTP within Google Cloud. So the first line says that Cloud Bigtable is not a relational database. That's a good thing. We have not marked that as one. It does not support SQL queries, joins, multi-row transactions. In the green box, I've highlighted if you need full SQL support for an online transaction processing system, consider Cloud Spanner or Cloud SQL. That's great. Those are the two that we have come to as the right choice for a transaction system. All right. The next one we need to consider is that our users are globally spread and we need to serve all of them. Looking at this, the two options that I have chosen are Cloud Spanner and Bigtable as something that scales globally. Now, BigQuery and Firestore, which is a newer version of Data Store, support what is called a multi-regional option. Today, that is either in Europe or in US. A multi-region is a large geographic area that contains two or more geographic places. So instead of choosing a particular region, there are some predefined regions chosen for you, and the data is going to be replicated in that multi-region. So this is not necessarily globally available, but it is available in, say, Europe or US to have a multi-region which covers a large area of that particular region. I have not chosen Cloud SQL as an option as yet because that also tends to be regional. Let us just look at the documentation on Bigtable global availability. It says that replication for Cloud Bigtable enables you to increase the availability and durability of your data by copying it across multiple regions or multiple zones within the same region. In another section, every cluster in a replicated instance accepts both reads and writes, providing multi-primary replication with eventual consistency. You can set up replication by adding one or more Cloud Bigtable clusters, whether on the same continent or halfway around the world. So Bigtable is good for global availability. How about Cloud Spanner? The landing page for Cloud Spanner reads out a few of the things we already know about Cloud Spanner. It has global scale, horizontally scalable across rows, regions, and continents from 1 to hundreds of thousands of nodes. It supports relational semantics and has ACID transactions and a relational database schema, which supports SQL queries. It also has transactional consistency, which is purpose-built for external, strong, global transactional consistency. So based on all of this, our choices on Cloud Spanner and Bigtable are great. As I said before, Cloud SQL is not a very firm option for me when it comes to serving users globally because Cloud SQL is more of a regional database. You can have replication across regions, but then it is a little more harder to achieve. Whereas for serving users globally, I am not very sure about that. This leaves us in a little bit of a quandary though, because based on this table now, we can see that Cloud SQL and Cloud Spanner definitely are ticked for relational database and as a transactional database, whereas on the global scale, Cloud SQL does not suit. However, given that we have to choose two products and none of the others qualify in any way, or they don't qualify for most of the requirements, we are going to choose Cloud SQL and Cloud Spanner. Now, it is not that Cloud SQL cannot be used globally. You can have users from across the world accessing Cloud SQL in one region, but then you're going to have more latency for international users. But given that we have to choose two within these options, these two, Cloud SQL and Cloud Spanner, are the best that I will have. What are the key things to study? You have to know the storage option flowchart thoroughly. by heart this. Let's also, while we are in this subject, see what are the differences between SQL, NoSQL, and what is called NewSQL. SQL databases are typically transactional databases. This is not necessarily true of every database, but the ones that are very popular today, MySQL, MS SQL, Oracle, Postgres, all of them are SQL and they happen to be transactional databases. Transactional databases follow ACID principles. But adhering to that means that it has reduced horizontal scalability. NoSQL databases came into existence so that they can have horizontal scalability and serve users across the world, but they have initially had to forego some of the ACID properties. An example in Google Cloud is Bigtable. NoSQL, as the name suggests, does not use SQL to access the data. Instead, NoSQL is a broad category of databases with different storage formats. It could be a document database, a JSON database, a key value pair. The data inside that is non-relational, and you will have to look at each database and its documentation to figure out what the storage format is. Examples of a NoSQL database within Google Cloud are data store, file store, memory store, Bigtable. NoSQL data is typically semi-structured. So there is going to be some structure to the data, like for example, JSON has a structure, a key value pair has a structure, and yet it is usually extensible. It is possible to have some key types defined in, say, data store and file store, but have different attributes for it inside that JSON or document. This is in comparison to what is unstructured data. Unstructured data would be like files, PDFs, Word documents, images, videos, music. Those come on the far right of what would be unstructured data. In recent years, there's been a new type of database called a NewSQL database. A NewSQL database tries to combine both the transaction processing and horizontal scaling, and a NewSQL database available within Google Cloud is Cloud Spanner. What are some of the other key learnings that we should take away from this question? You should know the global availability of storage options. Are they regional or are they global? Within each storage option, it's important to know the ceiling for the size of stored and processed data. Up to what amount of data does it perform well, and after what point is there a degradation in performance? Certain storage options like Bigtable will not have will not have a degradation performance provided you keep on adding nodes. So those scale linearly. Whereas certain others like MySQL will hit limits in and around terabytes of data. You should know the difference in these technologies. What is a relational versus a non-relational database? What are the differences between SQL, NoSQL, and NewSQL? How is an OLTP different from an OLAP? What is structured, semi-structured, and unstructured data? And which of the storage options support which of these? Know what is a regional, a dual regional, or multi-regional availability for different storage options, including for unstructured data like cloud storage and file store. Also know what are ACID transactions and what each of them stand for. With that, I will leave you with a few references on Cloud Spanner, on Bigtable, on replication of some of these technologies, including Bigtable and Cloud SQL, and some of the Wikipedia articles on database transactions and relational databases. Now it's time to subscribe to all the great content we've got lined up for you to learn Google Cloud and to help you with the certifications.
you.